Hybridization is simply defined as mixing of atomic orbitals to form bonding or molecular orbitals. These newly formed bonding orbitals have the same energy. They are equivalent. The first example I go after is methane. Methane is CH4. When you do the Lewis dot structure, you realize it's a tetrahedral in geometry. There are 4 single bonds. All these single bonds are sigma, which is axial or head-on overlap of orbitals. Now, in order to describe this shape, let's just look at carbon in its ground state, meaning when it's isolated and not formed into a compound. Carbon has 6 electrons, 4 of them being valence. 1s2 has the lowest energy, spherical in shape, 2 electrons. Then at higher energy you have 2s2, 2 electrons there, opposite spins. Then 2p, slightly higher, and don't forget p has 3 orbitals. 1 electron into each of the vacant orbitals due to Hans. Now we are going to mix this, and that mixing we are going to call hybridization. So mixing of orbitals, hybridization, simply mixing. Now you don't need a 1s2 because its inner electron not going to participate in bonding. But the 2s and 2p are going to mix, and they will form same energy hybridized orbitals. You will form 4 orbitals. Each one of them will be known as sp3, sp3, sp3. Into each of these orbitals you have 1 electron. So now you have formed 4 orbitals that have the same energy, same shape, and they are ready and willing to accept 1 electron from each hydrogen. So this is 4 sp3 hybridized orbitals. These are your molecular orbitals or bonding orbitals. One other thing you should realize that sp3 means you have a 25% S character and you have 75% P character. Although they are equivalent, but they will have mixture of your original orbitals. If I try to draw the shape, carbon is here with 1s2 spherical. The newly formed orbitals have lobes like this. So a tetrahedral geometry comes to life. Now each of the hydrogens, I'm going to put them in red, are going to come here and put their electrons into these newly formed orbitals. So 2 electrons, 1 belonging to hydrogen, 1 belonging to carbon. 2 electrons, 2 electrons. Now this is also a sigma bond. So you have 4 sigma bonds, and it's a head-on overlap of s orbitals and the newly formed sp3 orbitals. So you have 4 sigma bonds. Sigma, sigma, sigma. So hybridization, if this is difficult, just go back to the definition. It's mixing of atomic orbitals to form newly formed hybridized or bonding orbitals. If you have 1, 2, 3, 4 attachments, then try to mix S and 3 P's, and you will have 4 sp3 orbitals that are hybridized. The next example I go after is Eita, ethene, C2H4. And if you do the Lewis dot structure of that, there is a double bond between carbons, then single bonds between hydrogens. Now this geometry is trigonal planar for each carbon. And before we try to describe hybridization, you have 1, 2, 3 attachment. Therefore you have S plus P atomic orbitals. That means you have sp2 hybridized. So each of these attachments are sp2 hybridized. Now once you have sp2, you should realize it's same as trigonal planar. So the shape and the hybridization are correlated. You should be able to go back and forth. Now let's go after carbon one more time. It's in its ground state. We decided that 1s2 has 2 electrons, 2s2, remember, has 2 electrons, 2p, 2, which has 3 orbitals, has 1 electron in each. Now this time when we mix, I'm only going to mix 1s and 2 p's as what I need. So I will form sp2 hybridized, sp2 hybridized, sp2 hybridized, 1 electron in each. Now one of the electrons in 2p is going to stay up there unhybridized, which is 2p sub z. Not important if you don't remember the plane, but it's z. So let me isolate this tree and say this newly formed orbitals are hybridized. And this one here is unhybridized. And we are going to see what happens to that one. So what I'm saying, this is a sp2, sp2, sp2. Now let's just look at the geometry if we can. So we have carbon here, 1s2, small sphere, and then you have a sp2 coming out, sp2 going inside the plane, and another sp2 here. Now let me put my hydrogens in red. So hydrogens, one is coming here, putting 1 electron into the sp2, the other one comes here, puts the electron into that. Now don't forget these are sigma bonds. So far you form 2 sigma bonds with each hydrogen and sp2 head-on overlap. Let me put my other carbon next to it, really close. And the same shape coming to life. And then I put my hydrogens into the head-on overlap and form 2 more sigma bonds. Sigma, sigma, and this one here, which is sharing of 2 electrons between the nuclei, is also sigma. Now what happens to the unhybridized? I'm going after that. This P will overlap above the axis of the nuclei. And this is a bond that is known as pi bond. Pi bond. So this is pi. Then you have 1, 2, 3, 4, and 5 sigma bonds. So sigma, 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 and then there is 1 pi bond which is above and below. Now this pi bond is slightly weaker, but since you have accumulation of 4 electrons between the nuclei, the double bond gets smaller in size compared to a single bond. Now let me go to the last example I want to do, and this time I want to go after ethyne or acetylene, which is C2H2. Lewis dot structure, you will have triple bond, the maximum covalent bonds that you can have in chemistry, triple bond. Now before anything else, you should realize you have 2 attachment, so carbon is sp hybridized. You should realize all single bonds are covalent, so I have sigma covalent here, sigma covalent, and then you have 2 pi bonds, 1 pi and another pi. Now let's just see where this sp hybridized comes from. We go after carbon one more time, ground state. So you have 1s2, 2 electron do not participate in bonding. You have 2s2 and you have 2p2. 2, 1 in each. Let's mix them up. So hybridization is mixing of atomic orbitals. Now I only need 2 sp. sp hybridized, sp hybridized, and I will have 2 of my p's unhybridized. 1 electron in each. 2p sub y, 2p sub z, 1 electron in each. Then again, I only mixed 2 that I need. So this is hybridized. 2 sp hybridized orbitals. And you should realize this 2 at higher energy, I didn't mix them, therefore they're not hybridized. Now I'll try to draw the shape for this. This is extremely difficult, but 1 carbon is here. This is a sp hybridized linear shape, and then I put my hydrogens. So the hydrogen comes here. And this is a sigma bond. So I already formed a sigma. Let me go after my other carbon. I draw it very close. And sp hybridized, sp hybridized. I'll put the other hydrogen on the other side. I formed a sigma bond here. And this interaction here between the 2 nuclei, 2 electrons being locked in there, that's also sigma. Now let's go after one of the pi's. So I'll go after this pi here, which is overlap of 2 orbitals. So this is a pi bond. Now if I try to draw the other pi bond, I will do it in another 90 degrees to that. So you have to use your imagination. So this is my second pi, this one here. So in a triple bond, you always have 2 pi, 1 sigma, and its overlap of unhybridized orbitals.